Hello, class. Today we're going to talk about the one sample t-test. We've already discussed ad nauseum what the one sample z-test is all about. And while that's a really good first test to learn and start with, it's not very practical. Very rarely are we going to be comparing one sample to one population because we very rarely will deal with populations within psychology. We're going to focus on a slightly more useful test. I don't think I've ever used a one sample z-test in my own studies, but I have used a one sample t-test. It is much more practical, but still not the most practical test. So we're getting a little bit more complicated, but a little bit more practical here with the one sample t-test. All right. So the first thing that we're going to talk about in this lecture, the t-distributions. We're going to mention what the t-distributions are all about. What are they trying to get at? Obviously, we switched from a z to a t, so what's all that about? Then we're going to talk about how to do a one sample t-test and give you guys a few examples of solving those problems. So t-distributions. The first thing to notice is that it is not a singular distribution like the z-distribution. The z-distribution is a single distribution. There is only one of them. Okay. T-distributions, there are many different types of t-distributions. And we'll talk about what thing distinguishes, how do they change? Okay, so t-distributions are distributions that look very similar to a normal distribution. In fact, they look very similar to a z-distribution, but there are some slight differences between the t-distributions and a z-distribution. So the first thing to talk about is that there are three major types of t-test. The one sample z-test, or one sample t-test that we're going to talk about today, the independent samples t-test, and the paired samples t-test. For one sample t-test, we are making a comparison between one sample and a population mean. So one sample mean, one population mean. But we don't know what the population standard deviation is. Ooh, that's problematic. Remember, the logic behind the one sample z-test is we want to draw the sampling distribution. Think about what the sampling distribution is going to look like under the null hypothesis. Now, we can't do that for a one sample t-test. How are we going to know what the population standard deviation is? We have to guess what it is. And the way that we end up guessing it is by looking at the sample standard deviation. Remember, one of the assumptions of a parametric test is that of homogeny of variances. That whatever means that we're comparing, that their variances are pretty much identical. So the sample variance or sample standard deviation should give us some insight as to what the true population standard deviation is. But sometimes we're going to be more accurate than others. Okay, think about it. What factor of our sample might determine how accurate our sample standard deviation is as predicting our true population standard deviation? Well, the more subjects that we have, the more accurate that sample standard deviation is when predicting the population standard deviation. If we have a few subjects, okay, that standard deviation might be off. It might be all over the place. It might vary a lot. But the more subjects that we have, that sample standard deviation, sample variance gets closer and closer to what the true population standard deviation, population variance will be. Okay? So we are going to use the sample variance or standard deviation to estimate what the population standard deviation or variance is. Now, there's one more useful thing that we can do with a one sample t-test. Instead of comparing a sample mean to a population mean, we compare a sample mean to a particular score. Let's say that we're doing a Likert type scale. And we want to see if people's opinions on a scale of 1 to 7 is significantly different than 3 or significantly different than 5. We can do that with a one sample t-test, and that's going to prove very useful in many situations. We'll encounter a couple of those when we do some practice problems. All right, we've got our independent samples t-test. This is when we're comparing two samples, and we're using a between subjects manipulation. We have a between groups design. So Maybe we have these people in the experimental group, these people in the control group. We're trying to see at the level of the population, are they different from one another? Are the population means truly different from one another? That's what an independent samples t-test is going to do. Our next module is going to be all about these. Then we've got ourselves the paired samples t-test. For paired samples t-test, again, we're comparing two sample means, trying to find out in the population, are they different from one another? But this time, instead of having a between subjects manipulation, we have a within subjects manipulation, or a within groups design. So everybody participates in the experimental condition, and we get their measure on the dependent variable, and then everybody completes the control condition, we get their dependent variable, and we're making comparison with everybody, their dependent variable in condition 1 and condition 2. So that's what we're doing here for a paired sample t-test. More about which later. That will be in 2 modules from now. So first thing that we're going to talk about are the t-distributions. So first, a little bit of a cool story. So how were the t-distributions discovered or created? Well, there was a famous head brewer of Guinness, a man by the name of William Seeley Gossett. And Gossett was very interested in statistics. In fact, he worked a little bit with Carl Pearson. He was good friends with Ronald Fisher. And he wanted to find a way to determine whether or not different concoctions of beer were more successful than others. So in doing this, he ended up creating these t-distributions and some of the first t-tests. Now, he does a little bit of it. He actually doesn't call it the t-distribution. That doesn't come till later, where Ronald Fisher really uses some of Gossett's research and really elaborates on it. And that's kind of the t-test that we use today. But Gossett was trying to find out, the best formula for beer, how to make Guinness the best. And he ends up coming up with these t-distributions, and he wants to publish them. But Guinness will not let him publish them, okay? Because if he ends up publishing it, well, then all the other beer companies are going to use the same technique, and they don't want it to be stolen. But Gossett is a scientist, and scientists want their information to be out public. So Guinness and Gossett come up with a compromise. Gossett ends up publishing under a pseudonym. So not his true name. He calls himself Student. So to this day, sometimes we call these a student's test, or we call them student's t-distributions. All right, and that's the pseudonym that Gossett ended up publishing under, which is a very humble thing to do if you think about it, right? You get all this credit attributed to Student, but it's not your real name. So how will ever people know about you in the future? Okay. And beer having a huge impact on statistics. You would not think it, but thus is the case. So here are our t-distributions. I want to point out that if you look at the dotted line here, the dashed line that goes all the way to the top here, that's our normal distribution. Our t-distributions are underneath it. Notice that they don't rise as high, and the tails of these distributions are fatter. Okay. Sometimes I refer to t-distributions as just normal distributions with more junk in the trunk, and sometimes that will get a laugh. Recently, I had to use the word thick with 2 C's to get students to be like, ha, 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 that's funny. But yeah, so t-distributions are just like normal distributions, except they have fatter tails and they don't go as high, okay? So that's what's going on here. Because we are less accurate with determining what the true population standard deviation is, our t-distribution has to reflect that inaccuracy. So the less confident we are, the more we're expecting scores, extreme scores, either to the left or to the right. So the fewer subjects that we have when estimating what the true population standard deviation is, our t-distribution is going to have a much fatter tail. It's not going to rise as high. The more subjects that we have, the t-distribution is going to raise higher, and it's going to have smaller tails. Okay. How do these t-distributions vary? Okay, what is the thing that changes the shape of a t-distribution? Well, I said it was the number of subjects, and that is true. But technically, the thing that varies is a term called degrees of freedom. the degrees of freedom of the t-distributions change. And degrees of freedom is a difficult concept, but you'll see it quite often in statistics. We abbreviate degrees of freedom DF. I know that doesn't look like a D and an F, but I promise it is. Now, degrees of freedom are the number of observations that are free to vary. So let's say that we already know an outcome. Let's say that we know that our mean is 10. And we know that we have, let's say, 5 numbers. And we know that the mean is 10. How many of these observations are free to vary? Well, this first observation can literally be anything. It could be 10, it could be 0, it could be negative 100, it could be 5 million. Okay? This observation is completely free to vary. Okay, as long as these other ones are something where the mean equals 10, this one is completely free to vary. Okay? How about this one? Okay? Is this number completely free to vary? Yes, it could be 5 million, it could be 2, it could be 17, it could be whatever it wants to be. Same thing with this one and this one. Okay? How about this last one? No, these numbers can be whatever they want to be, but this number has to be something specific for the mean to be 10. So this last number is not free to vary. So in this situation, our degrees of freedom is equal to the number of subjects that we have, or the number of observations that we have, minus 1, because that last one cannot vary. Okay? So that's just kind of an example of what a degree of freedom is, but it gets a little bit more complicated than that. Okay, so as our degrees of freedom go down, okay, we see that the height of this distribution goes down and the height of the tails goes up. These are arrows, I promise. Okay, let me get out of drawing mode here. So when we use the sample variance to estimate the population variance, we must first estimate the mean. With the mean known, there are n minus 1 points that are free to vary. Okay, that's the same thing that I mentioned beforehand. As the degrees of freedom increase, the t-distribution gets closer and closer to what the standard normal distribution looks like, or the z-distribution, same thing. Okay, yeah, it gets closer and closer, it approximates, and in fact, with infinite degrees of freedom, the t-distribution is identical to the standard normal distribution. We'll see that here in a second. Ooh, this is probably a better graph than what I have here. So we have here in the gray line, the standard normal distribution. Also the same thing as t with infinite degrees of freedom. With t this is the t-distribution right here when we have 13 degrees of freedom. Notice it doesn't rise as high, and notice that the tails are fatter than the standard normal distribution. And then we have yet another t-distribution where we have very, very few subjects, 5 degrees of freedom. We see that this distribution is very squat, okay? So that distribution is very squat, very low to the ground, has very fat tail. Okay, so we're going to use the t-distributions this time to help answer our questions about do we accept, not accept, do we reject, or do we fail to reject the null hypothesis? We never accept the null hypothesis. Okay, so let's do some examples of this. So what happens when we do not have the population variance? So let's say the national average of college food satisfaction is 2 on a 7-point Likert scale. Pretty low. College students don't really enjoy the food options that they have on campus. We do not have the population variance. Okay, we don't have what that is. And we take a sample of 21 people from Dahlonega. Okay, the Dahlonega campus at UNG, and find a mean of 3.5 with on that scale with a variance of 4. Okay, so let's go ahead and write down all the information that we have here. Okay, we have a population mean of 2. We have an N of 21. We have a sample mean that's equal to 3.5. And our standard deviation, or our population variance, my apologies, is equal to 4. So our standard deviation we know is going to be equal to 2. Okay. So let's continue here. So is there a difference in college food satisfaction between the national average and Dahlonega? I wanted to leave this information up here so that we know what kind of test is this. If I'm asking, is there a difference? I'm asking that, well, we know it's going to be a two-tailed test. Okay. Lovely. All right. So how do we do this? Well, let me tell you, everything that we're going to do is going to be very, very similar to the one sample z-test. In fact, you might not even really notice a difference at all. There'll be two major, two minor differences, and that's pretty much it. So since we don't have the population variance, we're going to have to use the sample variance for UNG students to approximate what the true population variance is. However, we cannot be 100% sure of the population variance, so we need to be more cautious about our conclusions. Okay, we need to be more cautious about our conclusions, and that cautiousness is reflected in the t-distribution. Okay, since the tails are fatter, okay, that means that the cutoffs for the t-distribution are going to be more strict. They're going to be harder to reject the null hypothesis than the standard normal distribution. So one way of saying it is that if we could use a one sample z-test compared to a one sample t-test, we have more power with the z-test compared to the t-test. It's harder to reject the null hypothesis for the one sample t-test. Okay, but in many situations we can't use the one sample z-test, so it's not a huge deal that we're not using it. And also, if we can use the one sample z-test, why wouldn't we use it? Okay. So let's go through the steps. Step 1, state the hypotheses. So our null hypothesis is the population mean at Dahlonega is equal to the population mean of the nation, the national average. I could cross this out and not use this, and I could just as easily say that the null hypothesis is the population of mean equals 2. Okay, that would be perfectly fine. If I have an equal sign here in my null hypothesis, well, I always have an equal sign in my null hypothesis. The alternative is the exact opposite. I'm trying to see if there's a difference, so I'm going to use the does not equal to. Okay, so let's state the statistical decision criteria. Alpha is equal to 0.05. Here's the first major difference here between the one sample z-test and the t-test. We need to write our degrees of freedom. And our degrees of freedom are n minus 1. So we have 21 subjects, that's our n, and so our degrees of freedom are going to be 21 minus 1, which is going to be 20. Okay, not too difficult right there. The kind of test that we're doing is a one sample t-test. Is it one-tailed or two-tailed? It's a two-tailed test, so I'll put that right there. And then I need to look up my cutoff values. So my cutoff values, where do I find those? Well, it turns out in that tables packet I gave you guys a while ago, we can find it. Okay, so in our tables, right after the standard normal distribution with all the z-values, we have a table that's called critical values for a t-distribution. First thing that we need to do is we need to look at our degrees of freedom and find the appropriate one. Then we need to determine if we have a two-tailed test or a one-tailed test, and if alpha is 0.05 or 0.01. Now, it's never 0.01 for us. It might be in another discipline, but it's not 0.01 for us, so we are never going to look at these columns, at least for this class. We're always going to look at the 0.05 columns, depending if we have a two-tailed test or a one-tailed test. So we have 20 degrees of freedom. Okay, and we are looking at a two-tailed test. So our cutoff values, our critical values, our t critical is going to be equal to plus or minus 2.09. My apologies there. Now, 2.09 is close to another number that you guys have familiarized yourself with. Okay, plus or minus 1.96. This is very similar to that. This is what it would be if we were doing a one sample z-test. Okay, if we were doing a one sample z-test, our cutoff values would be above positive 1.96 and below negative 1.96. Okay, but we're doing a t-test. We need to be more cautious. So this cutoff value is going to be a little bit larger. Okay, so it's going to be plus or minus 2.09, and I'm finding that here in my table. So notice that as the degrees of freedom increase, the cutoff value gets closer and closer and closer to what it would be under the one sample z-test. So it starts off super large, and it's going to get closer and closer and closer to 1.96. For the one-tailed test, it's going to get closer and closer and closer to what? 1.645. That's the other value I got you to memorize. So let's see this. As we go closer and closer and closer, as we get more and more subjects, notice that the cutoff value gets to be exactly the same as the z distribution. It's 1.96 and 1.645 here. Okay, I'm extending it a little bit because the 5 is a little bit more accurate there. But those are our cutoff values if we were to have infinite degrees of freedom. Okay, if we have infinite degrees of freedom, we have infinite subjects, so we have pretty much the population. Okay, let's get rid of that and get right back on track. Whoop. So our cutoff value is plus or minus 2.09. All right, here's a question for you guys. If I have a value that's 1.50, what do I do with the null hypothesis? I retain it because it's in the middle here between negative 2.09 and positive 2.09. How about if I have oops, let's just say that that's, how about negative 2.00? Do I retain or do I reject the null hypothesis? Again, I retain. It's within this value. It's not lower than negative 2.09. How about if I had positive 6.4? Well, that's greater than positive 2.09, so I would reject the null hypothesis. How about if I had negative 3.1? Okay, that's lower than negative 2.09. So again, I would reject the null hypothesis. I'd reject the null hypothesis here. I would fail to reject or retain the null hypothesis right here. Okay, so now we're going to do our statistic. And our statistic is going to look quite similar. Ooh, look at this. Okay, T equals the sample mean minus the population mean. That's the exact same thing as the one sample z-test. And in the denominator, we have the square root of the sample variance over n. Now this is exactly the same thing as the one sample z-test with one exception. Instead of having the population variance here, I have the sample variance. That's the only difference. And I could write the denominator another way. If I wanted to write the denominator this way, the sample standard deviation over the square root of n, I'd be perfectly good. I'd be perfectly happy with that. Minor thing right here. Is it okay to use big N or is it okay to use little n? Which one of those should we be worrying about? Right now, it doesn't matter. Okay? Right now, big N and little n are the same thing. But soon, we're going to need to make a distinction between the two of them. Big N refers to the total number of subjects in the entire study. Little n refers to the number of subjects in a particular group. Right now, those numbers are the same thing. But when we look at an independent samples t-test where we have two different groups of subjects, well, we need to make a distinction. So that's coming up, and I want you to be prepared for that. Okay, so let's do our math here. T is equal to 3.5 minus 2 all over the square root of 4 divided by 21. We get 1.5 divided by 0.436, and this number is 3.44. So this is larger than positive 2.09. So what do we do with our null hypothesis? We reject it. Okay, and we reject it. We say that there is a significant difference between people that are eating at Dahlonega, their satisfaction, compared to college places as a whole. I actually don't mind the chow hall that much. You guys seem to mind it a whole lot more than what I do. But I don't know. I guess if you have it very, very frequently, you probably less don't like it nearly as much. All right, are we done? The answer to that question is no. Now we know how to do effect size. So we need to make sure that we include effect size for this problem as well. And the effect size that we're going to use, since we're comparing two means, is Cohen's d. Cohen's d is very, very similar to how it is for a one sample z-test. The only major difference here is what's in the denominator. Instead of having the population standard deviation, we have the sample standard deviation here. So let's calculate this. Well, the sample mean was 3.5. The population mean was 2. The sample standard deviation is 2. So 3.5 minus 2 is 1.5 divided by 2, which should give us a Cohen's d of 0.75. I'm trying to impress you because I'm not looking at my answers. Let's see if I'm right. Boom! Math in my head. So our Cohen's d is 0.75. What would Jacob Cohen say about this effect size? He'd say that it's a fairly large effect size. Okay, well, he would waver and say, what discipline are you in? But according to how most people use his suggestions, this would be a fairly large effect size. All right, so now let's do our step 4, our favoriteest step in the entire world. So let's write out what we have here. So we reject the null hypothesis in favor of the alternative that the food satisfaction ratings population means, so we're talking about population means right here, for UNG students, I give the mean, I give the standard deviation, does not equal 2. Okay, I could say does not equal the national average, and then in parentheses put population mean equals 2. That'd be fine. Both things are fine. So we have T. Ooh, here's something new. What the heck is this thing right here? As I occlude it with my arrow. That thing is the degrees of freedom. Okay, what we're going to do now is instead of just saying z equals blah, t, we need to specify the degrees of freedom. We're going to put the degrees of freedom in parentheses, and then we're going to say what t is equal to. So, let me exit on this. Okay, t with 20 degrees of freedom is equal to 3.44, comma, we're going to give the p-value. We don't know because we didn't calculate an SPSS, but we know that the p-value, if we reject the null hypothesis, is less than 0.05. So that's what we're going to do here. How about Cohen's d? We're going to end the statistic statement with our effect size. Here we're going to do Cohen's d, and it's going to be equal to 7.5 or 0.75. 7.5 would be a very large effect size. So we could write it this way, or we could write it in terms of the sample mean. So we reject the null hypothesis. Okay, I'm being fancy here. I've included that you could, if you really wanted to, include the statistical test early on when you write your step 4. When you write papers, this is a common way of doing this, but you don't have to do this. I just wanted to show you that. So we reject the null hypothesis in favor of the alternative that the food satisfaction ratings sample mean for UNG students, mean is blah, standard deviation is blah, is significantly. Notice that when we talk about sample means in our step 4, we need to talk about a significant difference from 2. And then I give the same spiel for what my statistical information is. This is how we would write it up in the results section of our paper. Okay, let us do a couple more examples here. So a clinical psychologist is interested in whether people who have lost a pet have moderate to severe depression. The psychologist administers Beck's Depression Inventory, a very famous measure of depression, to 41 people who have recently lost a pet and get a mean of 21 with a variance of 15. Do those who have lost a pet on average have a Beck's Depression Inventory score of 20 or higher? Okay, 1 second here. Okay, so let's write down all of our information. We have an N of 41. We have a we have a sample mean of 21 and a sample variance of 15. Where's our population mean? It's not there. Okay, we're not comparing this to a population mean, but we can still use the one sample z-test, or one sample t-test. Sorry about that. Okay, we're trying to see if the population mean of people that have lost a pet is greater than 20. Okay, is greater than 20. So we can treat this 20 as if it were a population mean, and we're trying to see if the sample mean is statistically higher than this 20. Okay, higher. What does that let you know? That lets you know that this is a one sample t-test. Not one set. Well, back up. It's a one-tail test. That's what I mean. Words are difficult today. I don't know why. But we have a one-tail test. So that's what we're going to do. Okay. So a little bit different here. Let us go through step 1, step 2, and all of those. Okay. 1 second here. Okay, sorry about that. I wanted to make sure I included something here. So I'm going to state my hypotheses, the population mean, and I could give it a specific value of people that lost a pet. Maybe I give it a sub-score or something right there, is less than or equal to 20 for the null hypothesis. And it's greater than 20 when we have people that have lost a pet. So notice here that I can't draw a population mean on the right here, really, because we're not comparing it to a population mean. We're comparing it to a particular score. So I have that score here on my null hypothesis and my alternative hypothesis. Alpha is equal to 0.05 degrees of freedom. We have 40 subjects, or 41 subjects. 41 minus 1 equals 40. We have a one sample t-test. It's a one-tail test. And if I go and I look at my table, let me go and look at that real quick. My degrees of freedom are 40. Okay. I'm doing a one-tail test, so it's going to be right here. So it should be positive 1.68. Okay. If it were less than, I'd have the negative 1.68. But I have the positive value because we're predicting that the sample mean is going to be larger than that particular value. All right. Okay. Sorry, I lost my PowerPoint, and I didn't want you guys to bear with me while I tried to define it. So our cutoff value is positive 1.68. So if we have a 2, we reject the null hypothesis. If we have a 3, we reject the null hypothesis. If we have a 1.5, we retain the null hypothesis. If we have a negative 1 million, we retain the null hypothesis, okay? Because it's a one-tail test. Negative 1 million is a very, very large effect, but we did not predict the effect would be in that direction. So we have to retain the null hypothesis. Okay. Let us do our t-statistic here. We have a population mean, or we have a sample mean of 21 minus 20, and we have the square root of the sample variance, which is 15, divided by n, which is 41. When we do this math, we get a t-value of 1.65. Ooh, so close, but no cigar. So do we reject or do we retain? We have to retain the null hypothesis. We have to retain the null hypothesis. We fail to reject the null hypothesis. We're not done. We've got to do Cohen's d. Okay, so we do the sample mean minus the population value, which here is going to be 20 because that's the score that we're comparing it to. And the sample standard deviation, we only have the sample variance, so we're going to take the square root of this. This is going to give us a Cohen's d of 0.258. That's a fairly sizable effect. I think Cohen would say that that's a small effect, but it's not something to like, I mean, it seems to be there. It just seems to be the case that we just don't have enough subjects to find that effect. We don't have enough power. Okay, so let's state our conclusion. We fail to reject the null hypothesis that the population mean for the depression scores after losing a pet, here the mean, the standard deviation, is equal to or lower than 20. Okay, we have to explain what the null hypothesis is when we fail to reject the null hypothesis. And then we're going to include our statistic statement. So T with the degrees of freedom, 40 is equal to 1.65. P is greater than 0.05 because we are failing to reject the null. And our Cohen's d is equal to 0.258. Sad we didn't find an effect, but thus is life. Another way of saying this, we could talk about things in terms of the sample mean. So we failed to reject the null hypothesis that the sample mean for the depression scores after losing a pet is significantly different or lower than 20. Okay, we failed to reject the after losing a pet is not statistically different or lower than 20. It's not statistically different or lower than 20. I made a mistake there. Okay, it should be not. I will correct that when I put the slides online. My apologies. Okay. Let's see what we've got. One more example here. A researcher samples 61 Southern high school seniors who have taken the SAT and compares the mean of sample SAT scores to the national average of 1,000. She hypothesizes that the sample SAT mean is significantly different than the hypothesized mean of 1,000. In her sample, she found a mean of 944 with a variance of 44,100. Okay. Again, let us see the information that we have here. Okay. Our N is 61. The national average is 100, not 100, 1,000. Significantly different means that we have a two-tailed test. I'm just going to write 2 here. And the sample mean is 944. And the sample variance is equal to 44,100. Okay. Written all my information down in my notes so that I can do this problem effectively. Okay. When I look at if something is different, of course, this lets us know that we're dealing with a two-tailed test here. So how do we do step 1? So step 1, our population mean. And these are, let me see, I forgot to look at the problem. Southern high school students. So I could do population mean in a lower thing that's like Southern students, so like SS or something like that, or South or something along those lines. Okay, is equal to, I could put the national population mean here, or I could just put the number of the national population mean, which is 1,000 in this case. The equal sign is always in the null hypothesis. The alternative always has the either the do not equals or less than or greater than. So this is good for step 1. Step 2, I have alpha is equal to 0.05. Our degrees of freedom equals 60. We are dealing with a one sample t-test. It's a two-tailed test because we're trying to see if there's a difference. And the cutoff value, if I look at my t-table, ends up being plus or minus 2. So if it's greater than 2 or it's less than -2, I reject the null hypothesis. Otherwise, I retain the null hypothesis. Okay, here is my t-statistic. Okay, so I take the 944 minus 1,000, and I take the square root of 44,100 over 61. And if I do my math, it ends up being -2.083. I'm going to compare this to my cutoff. Just barely, just by the skin of our teeth, we have gotten a significant result. Okay, so we reject the null hypothesis. Again, we're not done. We need to calculate Cohen's d. So here we are going to calculate Cohen's d. I'm looking here what the sample standard deviation is. It's apparently when we take the square root of 44,100, it gives us 210. So this gives us a Cohen's d of -0.267. How do we write this up? Well, I've just decided to write this up one way here. The null hypothesis was rejected in favor of the alternative hypothesis that the population mean of SAT scores for Southern high schools is different than the population mean score of all high school schools. And look, I did the population mean right here. T with the degrees of freedom, which is 60 and not 6. I really messed up a couple of places here. I'll make sure I fix that. Equals negative 2.083, comma, P is less than 0.05. Oh, no, it's not. It's greater than 0.05. Okay, because no. I'm confusing myself. It's less than 0.05 because we did reject the null hypothesis. And Cohen's d is equal to negative 0.267. Okay, cool beans. One more thing that we need to talk about before we end this lecture, and that is, well, two more things. Confidence intervals and what happens when you have a degrees of freedom that isn't on the table. Okay, so what happens when we look at our table and we have like 31 degrees of freedom? Okay, there's a couple things that you can do. Okay, one, you can look at a more advanced table than this and find out what that cutoff value is. Not necessary. Two, you can try to interpolate what that cutoff value is by looking at, okay, well, we have 31, so the cutoff value should be between the cutoff value for 35 degrees of freedom and 30 degrees of freedom. And there's a mathematical formula that you can do for that. Those are fairly complicated. Let me tell you a simpler way. Go with the cutoff value for the fewer degrees of freedom, okay? So if you have a 31, do the cutoff value for 30. If you find a significant difference there, well, then you're going to find a significant difference for the more accurate cutoff value, okay? The more degrees of freedom that you have, the more power you have to detect an effect, okay? More subjects that you have, the more power that you have. So if you can do it with a smaller number of subjects, hey, good job. You have found a true effect. Okay, you're gonna reject the null hypothesis if you were to have the correct, the specific cutoff value. So that's what I want you to do here. Okay, so what you should do is, if the effect is borderline, you might want to look at a more advanced t-statistic. But if you reject it at the lower degrees of freedom, you definitely have found an effect there. Okay, so confidence intervals. Confidence intervals are very, very similar for one sample t-test as they are for one sample z-test. Okay, the formula is exactly the same, but instead of the multiplying the standard error by z critical, which is either 1.96 in the case of a 95% confidence interval or 1.645 in the case of a 90% confidence interval, you are going to look at the t-table to find what the particular t-critical value is. Sorry. So that's what you're going to do. And with that critical t-value, you can use it to create the confidence interval. Okay. So let's say that we want to calculate a 95% confidence interval for our last example. So we've got 61 high school students. We've got a sample mean of 944 and a sample variance of 44,100. Okay. We know that the cutoff value is 2. Okay, and we need to calculate what the standard error of the mean is. So that's going to be the square root of 44,100 divided by 61. And this is going to give us 26.888. So to calculate this, we're going to, for the lower bound, take 944, subtract it by the standard error, multiplied by 2, which is that critical value for t. And for the upper bounds, we're going to take 944 plus that same expression. And this is going to give us a confidence interval of 890.224 to 997.776. Okay, that would be our 95% confidence interval for this statistic. If we were just caring about do we reject or do we retain, we could see if the population mean 1,000 is within the confidence interval. And since it is not, we would reject the null hypothesis. So 2 ways of finding out whether or not you reject or fail to reject the null hypothesis. You could do it with confidence intervals. You could do it with the more traditional statistical test. Both of those work. Confidence interval does give you some more information here with that interval estimate. Okay, a lot of information. Hope that made sense. I will talk with you guys later. Have a great day. Bye-bye.